Okay, so hopefully everybody found the homework on Teams okay? Yes? No? Yes. Yes. I got one yes. How about the rest of you? Okay, I'm going to have you raise your hand. If you found the homework on Teams okay, raise your hand. Yay. Okay, and if you did not find it, then we just need to go to homework, and there it is. Okay? So over in our channels, we've got our main channels, and then there's the homework. And if you've had me before, you know there's also a channel called Lesson Videos. And so yesterday's lesson is now up there. Okay, so how to name acids. It's block 4s. I'm recording today's lesson for you guys, but I'll only post one of them. Whichever one I do a better job in, I think I will try and post. Or if I forget to do it in one block, I'll post the one where I remember it. Okay? All right. So in our foundations unit, we have on page, fundamentals unit, we have on page, there's no page here. What the heck? Did I not paginate this? What? Oh, yeah. I don't know why this doesn't have a page on it. It'll be on page like 1 or something like that. So this is in the fundamentals. So that's the one that's stapled together. Okay, the white one that is stapled together. And this particular worksheet is optional because you learned this over the summertime. But if you feel like you have forgotten the rules for significant figures, you may do this. So this is optional. Okay. And today what we're going to do really quickly is, and I think most of you are probably good with this already, and there was no need for me to print out all this nonsense, but you know, we're going to do it just really quickly anyway. So we're on 1.1b, which is on page 3, I believe. Yes. And on your calculator, just to make sure you all know what button you're looking for when you're doing scientific notation, we have the button that says EXP, we have the button that says EE, or we have a button that says times 10 to the X. How many people have been using this button already? About 3/4 of you. Okay, if you're not using it already, this is the button you want to use for scientific notation, okay? And you do not want to use times 10 to the power of 23 or with a little x to the y, okay? And the reason you don't want to do that is because it will cause you problems in calculations later. Plus, you have now typed in 1, 2, 3, 4 keystrokes instead of 1 keystrokes, and that's just inefficient. And I don't like inefficiency, so you shouldn't either. You won't have time to type that much stuff. So make sure on your calculator you know where that button is, okay? And you'll want to pull out your calculator now because we're going to do a couple of things with this to make sure that we're good. Okay. EE. Sometimes your EE button will be like a second function and you have to press second and then EE. Here's the great big math calculator if you happen to have that one. It's a second function here. Don't use the caret. Don't use the log. And I can turn this off because it's not doing anything there. All right. So this is our magic button. And here are some common calculator errors, and we are now on page 6. Okay. I've never actually printed out this much stuff before of like the sort of basics for Chem 11 Enriched, but I was like, okay, I'll give it a go. I feel like I wasted a lot of paper. However, that's all right. So now that you have your calculator out, and if you don't, you're getting your calculator out. And if you have your phone on your desk, remember your phone has to be in your bag and on silent. Yeah. And if you don't have a calculator, I do have a few here. Okay, and you can try one of those. Any of them will do. Yeah. Anyone else need a calculator? I think some of the ones in the back are a little wonky, so I would take ones nearer the front of them. Oh yeah, okay, so you don't want that one, so I need to get rid of that. So now on your calculator, I would like you to type in 4 divided by 2 times 10 to the 3. So you want to actually type in 4 divided by 2. And then I'm just going to put an E, which stands for either the EE or the EXP or the times 10 to the X. And then 3. And if you're having trouble doing that, call me over and I can help you out. Anyone need a hand with that? Okay. Now I'd like you to try typing in 4 divided by 2, and then a multiplication sign, and then a 1, and then a 0, so times 10, and then either the caret or the x to the y, and then a 3. So try typing that in and see what you get. Do you get the same answer as before? No. Why not? What does your calculator think that you're doing? It thinks you're multiplying by 10 to the 3 rather than having the 10 to the 3 in the denominator. Okay? So it thinks you're multiplying by 10 to the 3 because calculators aren't that smart. You could fix this if you wanted to by putting brackets around the whole thing. Okay, so you could say divided by bracket 2 times 10 to the 3. But now instead of typing 1, 2, 3 keystrokes, you have typed 1, 2, 3, 4, 5, 6, 7, 8 keystrokes. Okay, and that just seems like a lot of work. So learn to use your magic button if you have not done so already. Okay, so for scientific notation, use that button. All right. I don't think we need to do this because it's the same thing. Similarly, if you're wanting to type in, and most of you probably already know this, but if you want to type in 24 divided by 3 times 4, I would like you to tell your partner what keys you would enter on your calculator to do that. Like, what would you actually type if you wanted to do that? So, the fastest way to type this in, well, first of all, the incorrect way to type this in is 24 divided by 3 and then times 4, because that's going to do the same thing. It's going to pop that times 4 up into the numerator. It's going to say 24 divided by 3, and then I multiply by 4, because that's how your calculator thinks. Okay? So you could do 24 divided by bracket 3 times 4. How could you save yourself some keystrokes? How could you make that shorter? Yeah?
Just do the 3 times 4 in your head and then divide by 4.
You could do that, but let's say we have some nasty decimal numbers in there, okay? And it's going to be a pain to do that in our head. You can just go 24, divide by 3, divide by 4. Okay? So that just makes life faster for you because you're taking 24 and you're dividing by 3 and you're also dividing by 4. Okay, so you go 24 divided by 3 divided by 4, and that will work nicely for you. Okay? So that is some little calculator tips to make your life easier. So I would like you guys to try typing this in, and remember you're going to use the E or EXP or EE, and you're going to go divided by 7.3 times 10 to the 5 and divided by 5 times 10 to the negative 4. So give that one a try and see if you get the correct answer. Oh, I forgot too. Don't use the minus sign. Like, don't use minus, or don't use subtract for the negative. You know how there's like plus, and then there's minus, and you don't want to use that one. What you want to use is you want to use either the one that says plus minus or the one that has brackets minus. That means turn it into a negative number. Okay? So don't use subtract, use turn it into a negative number. Yes. Yes, that's the one. And if you have trouble finding the button on your calculator, call me over. I can help you find it. Anyone want a hand with their calculator? Anyone having any difficulties? We're good? Okay. If this makes you uncomfortable, you can use the brackets. If you're like, this divide by thing makes me unhappy, feel free to stick those brackets in and just use them, okay? As long as you're getting the right answer, then it's fine, okay? Sometimes people get really excited by this button, but they try typing in the 7.3, and then they'll do times 10, and then the EE. You really don't want this times 10 in there because the times 10 is part of the EE or the EXP or if you have the button that literally says times 10 to the X, you can see that it already has that times 10. Yes? Is good? Okay. Is it just me or is this class quieter than the other class? Yeah. And there's only like 15 of them. So you guys need to up your game a little and interact a little more. I know it's first thing in the morning and you're probably still asleep, but okay. Where were we at? Oh yeah, here's where I went into don't use the minus button, use the plus minus. Sometimes there'll be like a little switchy over key, but you just want to make it negative. You don't want to subtract it. Is there anything else in here? Ah, yes. So you remember that. You remember when you were doing these calculations over the summer and you were converting between metric things. Now, if you have a 10 to the 3, and this is on page 9, Okay, page 9. If you have a 10 to the 3 and there's no 1 times 10 to the 3, there's 2 ways you can enter this in your calculator. I like to type 1 times 10 to the 3. So I'll do 1 EE3 or 1 EXP3 or 1 times 10 to the 3. That's how I will type it in. That's my favorite way of doing it. For when it's not scientific notation, because is this scientific notation? No, because scientific notation needs a coefficient. It needs a number in front of the times 10 to the. In this case, you can, if you want to, you would type in your times, and then you would type in your 10, and then you could use the little caret and the 3. Okay, because that raises 10 to the power of 3, and because it's not scientific notation. Personally, I find that students sometimes get confused when they're sometimes using the caret and when they're sometimes using the EE button or the EXP button. So I like that. Okay, so why don't you guys try typing that in on your calculator? This one right here. And see what you get. And I know probably you can do this in your head also, which is also an option, but let's see if you can do it on the calculator. Anyone having any troubles not getting it to work? We're good. Same thing? Okay. Good stuff. Now, of course, with something like this, if you wish to do these calculations with powers of 10 in your head, you certainly can. And it can be quite an efficient way of doing it because on the top you have times 10 to the 3 and in the denominator you have times 10 to the 6. What do you do with your exponents when you have one in the numerator and one in the denominator? Yes?
Maybe flip one, like just flip the fraction so they both on top.
Yeah, you can flip the fractions so they're both on top. If you do that though, you have to change the, you guys know this? The sign. Yes? If you divide by 3 to the 6, that's the same as multiplying by 3 to the negative 6. How many of you are familiar with that exponent rule? Okay. Most of you, maybe a little bit, maybe it's a little rusty. Yeah, okay. So let's just make sure that we're clear on that. So what I could do here is I could say, if I have something on the top, let's say I wanted to move it down to the bottom, okay? I could say now, I don't know why I would want to do that, but let's say I did, okay? When I move the 10 to the 3 down to the bottom, that's going to become 10 to the negative 3, okay? And that would still be, and that would then be 1 meter. And let's say I wanted to move this 10 to the 6 to the top. I would say, okay, I have 10 to the 6 micrometers is equal to 1 meter. Yes? Can you what? You can use other conversion factors. I'm just showing how to play with powers right now. Okay, so there's no worries about about that kind of thing. Let's just pretend there's no actual units in there and you're just mucking about with the powers of 10. Yeah? Another thing that you should know about exponents, if you had 3 times 3 to the power of 2 times 3 to the power of 6, that would equal 3 to the power of 8, okay? Because it's 2 plus 6. How many people are familiar with that exponent rule? Okay, again, most of you. All right. And if you're not familiar with the exponent rules, let me know. And I actually have like a sheet on exponents that I can give you. Like if you're like, whoa, what happened today? Like, I just don't know. Let me know. I can run one off for you and have it for you for tomorrow. Okay. So we got that. And if I have 3 to the 2 divided by 3 to the 6, that would be 3 to the what? -4, because it would be 2 minus 6. So if you've got something on the bottom, you subtract it, okay? So those are rules that you should, in theory, know. If, like I said, if you need a little review on that, let me know. I can find something for you. So if I have this equation here, I could do it in my head and say I have 10 to the 3 over 10 to the -6, which is 10 to the 3 minus -6, which is 10 to the 3 plus 6, which is 10 to the 9. Yeah? But you can do it on your calculator if you prefer to do it that way. You can do it in your head if you'd like to do it that way. And question, is this in correct scientific notation? No, what's wrong with it? Yeah, in scientific notation, you can have only one non-zero digit. You need one non-zero digit in front of the decimal. Actually, I should say one and only one. Okay, that's what I was trying to get with the only one. You need to have a digit there. It can't be 0 and it can't be bigger than 9. Yes? So here we have 13. Do you know how to change this number into scientific notation? See if you can tell your partner how you would do that. All right, anyone want to tell me? We move our decimal one place to the left, so it becomes 1.37. Did this number get bigger or smaller? It got smaller. And how many powers of 10 did it get smaller by? Smaller by 10 to the 1. So in order for this thing that's multiplied together, if 1/2 of the multiplication gets smaller by 10 to the 1, the other half needs to get bigger by 10 to the 1. So that's going to be now times 10 to the 10. Okay, so this got bigger by 10 to the 1. Okay. All right. On your calculator, not using scientific notation. Okay, never mind. There's some exercises here that you can practice just to make sure that you know what you're doing on your calculator. Again, this is I feel like this is kind of a thing that could be optional. Okay. So 1.1a, the exercises are optional. 1.1b, the exercises are optional, because some of you may feel like, oh my gosh, why would you do this to me? But just take a look at them and see, maybe if you're like, I don't know, do I need the exercises? Maybe you like, I'm going to try like these 4 because they look like they're near the end, and usually the ones near the end are harder. Okay, you are in charge of your own learning this year. I was talking about stress management with block 4. And one of the things that we talked about is that a lot of you have many academic courses. Yes? Okay. So if I give you an assignment and there's 15 questions in it and you just don't have time because you need to sleep and you maybe need to get some exercise and do things which are good for your mind, right? And your body, don't do all the exercises. Maybe do every other question, or maybe only do 5 of the 15, do every 3rd question, something like that. Make your life manageable for yourself. Okay. We also did yesterday, we looked at a study technique. Would you guys like to look at it today? It's called the Pomodoro. So we're going to do that. Okay, let's see. Study techniques. And we want the Pomodoro. Here we go. Oh, I don't want Bing. Bing is stupid. Bing gives me ads. It doesn't know who I am. Okay, Control C. There we go. Turn that on. I think he probably got paid to plug this app, but there's any number of apps that will do a Pomodoro, or you can just set a 25-minute timer. Okay. So this gives you a 2-hour study cycle, okay? Now this guy's in med school, so obviously he's studying 2 hours, but you guys are taking a university level course, and some of you are taking several of them, right? Because Physics AP1 is a university level course, and yeah, I don't know, some of you are taking crazy level math courses and stuff like that too. So you might find that on a weekend where you've got tests coming up all the next week, you might need to study 2 hours, 4 hours, whatever in a row. And this technique can make it more manageable to do that. So if you're interested, there is a link up there in this one where you can go and see all the things he does to study. We're not going to watch all of them, but you can go investigate that if you like. Okay, so he just says more about, change it for what works for you. For example, with my grade 9s, sometimes, they are very distractible. And I'm like, okay, do like 15-5, right? Because they could maintain 15 and then have a 5-minute break. And some of them love that, right? They're like, okay, I could do 15 minutes, right? So that was good. All right. Anyway, that's one technique that can help life be more manageable for you. All right, teams, bye-bye. Okay. Adding and subtracting in scientific notation. You don't have to do a lot of this. So quite frankly, if you never get this, it's not like the end of the earth. This is now on page 12. Okay. Adding and subtracting in scientific notation. You are going to use a calculator for the coefficients only. All right, you cannot simply take a number in scientific notation, add it to a different number in scientific notation, and hope to figure out what the significant figures are. Okay, if you just want to add them and you don't care about sig figs, that's fine. Okay, it'll work perfectly. But if you want to know what your significant figures are, you have to do it this way. Okay. So how it works is very much like a math problem where you have 4x plus 2x equals 6x. And how could we factor out these coefficients? Well, we could take the 4 and the 2 and factor them out. So we have 4 plus 2. Okay, 4 plus 2x gives us 6x. And when we are doing scientific notation, the coefficients are going to be the things that we factor out. So we're going to factor out the 4 plus 2 and keep the 10 to the 3 by itself. So now we have 4 plus 2, okay, times 10 to the 3, which gives us 6 times 10 to the 3. And this works beautifully as long as your powers of 10 are the same, okay? So we could take This next one, we could factor out the 4.5 and the 1.75 because these are both 10 to the 4. We add the 4.5 and the 1.75 and get times 10 to the 4, and there we are. Now, let's say we wanted to do significant figures for this question. How many sig figs in 4.5? 2 sig figs, but we're adding and subtracting, so does it matter how many sig figs? What actually matters? Your uncertain digit. So your uncertain digit is here, and for the other number, it is here. So we have the tenths and the hundredths. So what should we round this number to? 6.3 times 10 to the 4. Okay? So that is our addition and subtraction rule, and we get 6.3 times 10 to the 4. Now, if you have different powers of 10, now you have a problem. You cannot just do it that way because when you start, the power of 10 is essentially moving the decimal place to different spots. Yes? So we can't say how many decimal places do I have? This is in the tenths position? Is this in the hundredths position? Because the decimal has been moved different places by these different powers of 10. So we have to make a common factor by making those powers of 10 the same. So you can choose either one. You can say, I would like them both to be 10 to the 3, or I would like them both to be 10 to the 5. I very often, for whatever reason, like to make them both bigger, like to the bigger one. So I would take this 10 to the 3 and I would change it to 10 to the, and you'll notice that my pen does this weird thing where it makes lines where it's not supposed to. I did not draw that line. I drew a circle. You'll just have to get used to it. I will erase it and fix it, but I think I'm stuck with it until I get a new computer because it seems to just affect this machine. So here we are. Okay, so we have 10 to the 3 is now going to become 10 to the 5. And did that power of 10 become bigger or smaller? It became bigger, and it became bigger by how many powers of 10? 10 to the 2. So what's going to happen to the 7.5? It's going to have to become smaller by a factor of 10 to the 2, which means how many places are you moving your decimal? 2 places, okay? And are we moving it to the left or are we moving it to the right? The decimal. We move it to the left to make the number smaller. So we have now 0.075 times 10 to the 5. By the way, we don't spend a lot of time doing this adding of things in scientific notation. I think I said that before, but it's something you could come across, especially when you go off to university. And so I need to have shown you at some point so that you're like, oh yeah, I've seen that before. Okay, so this just walks us through what we just did. And now we have our coefficients, our powers of 10 are the same. And now we add our 0.075 to our 5.25. And that means our uncertain digits are in the thousandths and in the hundredths. So our uncertain digits are in the hundredths and the thousandths. So we need to round this to 5.33. Okay? There we go. Now, you could do it the other way. This just shows that you could have made the power of this 10 to the 5, you could have made it smaller. This would decrease by 2 powers of 10. 5.25 would have to get bigger by 2 powers of 10, so it would become 525. You add them the same way. We have a 0.1 position and a 1 position, and we get this number here. Is this number in scientific notation? No. It is absolutely not in scientific notation. What do we have to do to our coefficient in order to put it into scientific notation? Move the decimal to the left. So we have 5.325 times 10 to that. And you're going to tell your partner what you think that power of 10 should be. You guys are awfully quiet for telling your partner what you think that power of 10 should be. If that coefficient got smaller by 10 to the 2, the exponent needs to get bigger by 10 to the 2. So it's going to be times 10 to the 5. Okay? So there we are. All your steps are there. There's another example if you want to go through it. This is just making sure that you know which of these two numbers is a bigger number. Tell your partner which one is a bigger number. Okay, we're going to vote. We're going to get you all involved here. You're either going to vote the first one or the second one. Okay? 5, 4, 3, 2, vote. No, you didn't. Okay. Then take another moment and chat with your partner and decide whether the first number or the second number is bigger.
Say it out loud.
5, 4, 3, 2, vote. The first one is bigger. Okay, good. All right. I figured you guys probably knew that. I just wanted to make sure it was there. Alternately, if you don't like that converting powers of 10, you can convert everything into standard notation, add it up, figure out your sig figs, and then convert it back into scientific notation. Does that make sense? So you can be like, I don't want to be like changing this power of 10 to a different power of 10. I'm just going to say that 7.5 times 10 to the 3 is 7,500, and my uncertain digit is in the hundreds. I'm changing my 5.25 times 10 to the 5 there, and then my thousandths position is uncertain. I have uncertainty in the thousands and the hundreds, so my uncertain digit is now in the thousands position. Is good? Do you have a question? No, you're good? Okay. Okay. There's some exercises here. Again, these are optional. So we have 1.1a, 1.1b, 1.1c are all optional. What the heck is 1.1d? Ooh, multi-step. We're going to talk about those later. We're not doing that today. All right, I would like to talk moles with you today. So we're going to go to the pink workbook. All right? So for homework, you have done 5.1a, 5.1b, and so let's just see. Tell your partner how much 1 mole of particles is. Okay, what's the number, everybody? Okay, what's the first digit? 0.02 times 10 to the power of 23. And if you have trouble remembering that 23, Do you remember how I told you the charges on your periodic table were as easy as 1, 2, 3 yesterday? This is also as easy as 1, 2, 3. Yes? Isn't that nice? Oh, so if you ever forget, is it 24? Is it 22? Is it 25? I've forgotten. It's as easy as 1, 2, 3. And then you just have to remember the 6.02. But you will use it so often, you will never forget it. And if you're writing the AP exam, if you take out your pink data sheets and you turn to the very back page, okay. Why are there coulombs? Because in grade 12 we do electrochemistry, but you don't need it this year. Okay, so, and in fact, look what they give you. Oh my gosh, they give you all those metric prefixes, so you don't need to know those. Yes, this is page 1. There are actually 2 pages. It's just the second page. We don't use any of that stuff until grade 12. Okay, so you get all of this, and you will notice here that we have, what, don't they have it? Where'd it go? Oh, there it is. Avogadro's number.
Why does it say mole -1?
Because it wants to mess with you. Because a mole -1, do you remember what it means when you have a negative exponent?
Flipped upside down.
It means it's flipped upside down. So what that means is it means that there are 6.022 times 10 to the 23, whatever it is, per 1 mole. Okay, because mole to the -1 means per mole. Yeah? Yeah? So if you ever see something times 10, like a unit times 10 to the -1, just make it +1 and put it in the denominator. Exactly. So speed of light equals m meters seconds -1. So that's going to be meters per second. Yes. Yes. Is good? Okay. So basically, anytime you see this -1, it just means that unit goes in the denominator. Okay? And guess what this is? This is starts with a C and an F. And you spent a lot of the summer assignment working with them. It is a conversion factor. And if you did the optional 5.1C yesterday, some of you did. This is on page 9 in the pink book. One mole of particles is equal to 6.02 times 10 to the 23 particles. Yes? And so now you have a conversion factor. So if I give you whoa, where did that go? That's crazy. If I give you a number of atoms, you can use this conversion factor here. 6.02 times 10 to the 23 atoms is 1 mole of atoms. And you can use that to find moles. If I give you a number of molecules, you can use that same conversion factor because 6.02 times 10 to the 23 molecules is 1 mole of molecules. And of course, if I gave you a number of donuts, you could convert that into moles of donuts. Yes? A little bit silly, but there we are. And if I give you moles, you can convert backwards. You just have to take that conversion factor and do what with it? Flip it upside down, depending on which way you want to go. Okay? So, actual homework that is for homework today is 5.1C. Okay? And I'm going to write it up here, because that way I won't forget. 5.1C. Yeah. No. But we're not going to dilly-dally there today. Today we are going to, how much time do we have left? We've got 20 minutes left. No, I want to go to, yeah, actually, here we go. Did I lie to you? I lied to you. We're going back to fundamentals. We have to. I'm sorry. I lied. 1.2D in your fundamentals workbook, that's on page 32. We need to know what hydrates are before we can do this. Okay, so if I was to show you this structure here, does this mean anything to you? You raise your hand if it kind of means something to you, if you've seen a structure like this before. Sort of. Okay, so there's a lot of you for whom this is sort of maybe not a thing that you're familiar with. This is a structure of an ionic compound. Ionic compounds act like this. They alternate positive, negative, positive, negative, positive, negative, positive, negative. And when you put a positive beside a negative, what do they do to one another? They attract. And so you'll notice that everywhere there is a positive, it is surrounded by negatives, and anywhere there is a negative, it is surrounded by positives, okay? When you get into crystals that have a 2-to-1 ratio or a 2-to-3 ratio, the structure becomes much more complicated, and we don't have lovely models built like this for them because it's just...
It wouldn't look like a cube, right?
It doesn't look like a cube. You get weird things happening, okay? You can look them up, but it's really hard to visualize in 2D space. So
that would be salt.
this is salt. This is sodium chloride, for example, or calcium oxide, something where you have a 1-to-1 ratio. However, for the purposes of just being kind to ourselves, we imagine that all crystal lattices just look like this to make our life easy. Okay, so even if there's some weird hexagonal structure with things branching off here and there, we're going to just pretend it looks like this. Okay? And you're all familiar with what salt looks like, yes? Salt is made of crystals. So this thing is called a crystal lattice. Okay, this structure here is an ionic crystal lattice. And you'll notice that they've labeled here, this thing right here is an ionic bond. So those are all ionic bonds where we have the positively charged sodium attracted to the negatively charged chloride.
What's the thing in the middle?
What's the thing in the middle? Yeah, what is that? Do you guys recognize that shape? Who looks like Mickey Mouse? What atoms put together look like Mickey Mouse?
Water.
Water. Okay, so we have a hydrogen, and we have an oxygen. So this is a water molecule, and there are little water molecules embedded in the crystal lattice. So let's say, for example, that these things here represent water molecules. All right, and the nice thing is they do a little bit, right? They got the two things on the top and the thing at the bottom. It's kind of convenient, all right? And this would be what we call a hydrated salt. Why is it hydrated? Because there is water inside it, okay? So we have water inside this crystal lattice. Have we turned this crystal into a liquid by adding water? No, it's still a solid. I don't know. Have you ever had brown sugar? Brown sugar? Yes. Okay. You know how it's like a little bit moist-ish? Okay. That's because that form of sugar gets very hydrated, okay? But most of these, you wouldn't even notice that there's any water in there. You'd just be like, oh, it's just like a crystal, just like regular salt. You wouldn't even know that there's water in there, all right? Now, this is our hydrate. We can either call it a hydrated salt or we can just shorten that to say it is a hydrate. Where did I put my pen? Did I put it back? I did. So this is a hydrated salt, also known as a hydrate. Now, the ionic crystal lattice is held together by what kind of bonds are these? Ionic bonds. There's no ionic bonds bonding the water in here, but something is holding them in there. And you may or may not have heard of these things before. They are called intermolecular forces. Okay? And the word inter, the prefix inter, does anyone know what inter means? If you go on an international flight, you're flying between two different nations, international. So inter means between. Okay, and if we have intermolecular, what would that mean? Between molecules. Now, I really wish they'd call it interparticulate forces instead of intermolecular forces because the ionic crystal lattice is not a molecule, okay? But we still have these forces, stupid pen, holding this water molecule in place. Okay, so those forces there, they're still positive because the water has a positively charged end and a negatively charged end. It's a little more complicated than I'm showing here, but these intermolecular forces okay, these intermolecular forces hold that water inside those spaces in the crystal lattice. Okay, and because intermolecular forces is a huge long word and it's tiring to write, we will often abbreviate it IMFs. Okay, so an IMF is an intermolecular force. Now, something you should know, ionic bonds are strong. Okay? If you heat salt, does it readily turn into a gas? Does it easily turn into a gas? No. You would need to heat it really, really, really hot in order to melt it, right? You can melt salt, but you have to be at about 1,000 degrees Celsius. Okay? So you can break an ionic bond by providing a lot of heat, but it's very strong, so it requires so much energy, it requires a very high temperature. But intermolecular forces are relatively weak, okay? They're strong enough to hold the water there. It's not like the water's going anywhere as long as we don't do anything to it. They're just happily sitting there and they're like, oh, I'm just held here by little forces. Isn't that nice? And then what would happen if we got a Bunsen burner and we put it underneath here and we started to heat it? What happens to particles when we heat them? They start to move faster, and all of a sudden, those intermolecular forces break, and the water comes out. And we're going to do a lab in the mole unit that has to do with heating this hydrate and having the water molecules come out, and you'll actually see steam coming off of the compound. Okay? So, the intermolecular forces are weak, the ionic bonds are strong, and when we heat it, and we've simplified it even further here, our model, so instead of having it be a 3D model, now we've only got a 2D model, okay? And we've got some waters in here, okay? And if we heat it, you can see we now have the salt all by itself, and the prefix "an," that's like a negating prefix. I don't know exactly what it means, but I think it's like without, okay? Without hydrous. What's it without now?
Water.
It's without water. So we have taken our hydrated salt that has waters embedded in the crystal, and we've heated it, and it has become the anhydrous salt. And what happened to the water? It evaporates out, okay? So we get water vapor. So this is a gas, and this is a gas, okay? So we have a solid hydrate, a solid anhydrous salt, and then we have gaseous water. All right? So that's what a hydrate is.
So what's the, say, like, if you have, like, HCl, like, you have H2O,
So
but, like, physically,
this is how it works, and we're getting to that. Okay, so if we have, and this is on our next page here, this is how we write the formulas. Okay, so we have an ionic compound here, yeah, and then we have the water. And you'll notice there's no number in front of the water, and what that means is that we have one water. So for every one of those formula units, we have one water. So if we actually go back to our little picture, you'll notice that we have, for every one CaSO4, how many waters do we have? I've got 2 CaSO4s. How many waters do I have? I have 2 waters. So it's a 2-to-2 ratio, which is the same as a 1-to-1 ratio, which is why here I have a 1. This coefficient in the front just tells me I've got 2 of those units. Yes, I have 2 hydrated calcium salt units. Okay? So this tells me I've got 1 water. And when we go to name it, we then need to be able to say, how do I tell you that there's 1 of them in the name? Can you guess? Mono. Okay, so we're going to again use those prefixes, mono, di. What comes next? Tell your partner what comes next. See if you can fill them out before I write them down. Mono, di, tri. What comes next? Tetra. And then penta, hexa, hepta, octa, nona, deca. Is good? Okay. Now, this little dot here, do you remember how the water molecules, now we're here, do you remember how they were held on by intermolecular forces? And so it was kind of a weak interaction. That's why the water isn't actually attached in the formula, but it's attached by that dot almost represents the intermolecular force. Okay? That's kind of how I think about it. I'm not sure if that was the intent of it, but that's how I think about it. Yes, of course. Yeah. The weak IMF. Okay, now when we write the name, we don't put the dot in it. We just call it, we have our cation here, which is ammonium. How would I know that if I didn't know that? Where would I look? On your pink sheet, on page 3. And I would say ammonium, where is ammonium? Oh, ammonium is one of my only 2 common positive polyatomic ions. Okay? And then the other one, I think it was C2O4. And so I would go down here and I'd say, where is C2O4? C2O4.
Oxalate.
Here we are. Yeah, oxalate. All right, so I can look that up. I've got ammonium, I've got oxalate, so the name is ammonium oxalate. And so I now have ammonium oxalate. I don't put a dot. You'll notice there is no dot in the name. Ammonium oxalate monohydrate. That tells us there's 1 water. 1 water.
1 water again?
1 water in ratio to the 1 unit of the crystal. So if you have 1 NH4 and 2 NH4s and 1 C2O4, you have 1 water. If we have Ca3 and 2 dot 2H2O, how would we name that? Ca is who? Calcium. And calcium is not a transition metal, so it does not use a Roman numeral. And then, well, who is N? Nitrogen. So that becomes calcium nitride. And then we have dot 2H2O. So this would now be named calcium nitride dihydrate. Okay? And so we have here, here's a nice one. I actually want to try this one. We have like 1 minute left. We can do this. We can do this. I'll put the homework on Teams because it's going to be more than that. It's that I don't have time to look it up right now. I'll put it on Teams. Are you guys good with that? You can check on Teams for what exactly it is. Perfect. Okay. How do I know the charge of iron? It's not in one of the columns where we know the charge. Pardon me? The compound has to be neutral. So how would we figure out what the charge is for this? You have to take a look. Yes, sorry.
You have to figure out the charge of phosphate.
You have to figure out the charge of phosphate. So you go and you look up phosphate, PO4, and you say, what is phosphate? Phosphate is
3 negative.
3 negative. Okay, don't get fooled by that little 4 there. That 4 means that we have a P with 4 O's attached. It doesn't mean we have 4 phosphates. Okay, if I had 4 phosphates, I'd have to do PO4, 4. Okay? So I have PO4, 3 minus. That means my iron has to be 3 plus to have that charges balance out. So now we have iron 3-phosphate tetrahydrate. Okay? And so I'm going to have you guys do pages 34 and 35. Now remember, there's 32 questions here. Do you need to do all of them? No, do as many as you need to feel good about it. If that means you do 3 of each type, that's fine. So, pages. One. And there's something else I want to do as well, which is 5.1D. There we go. That's your homework. There we go. Feel free to take a picture. You can take out your cell phone and take a picture if you want to. It will be on Teams. All right. Oh, so the 5 is the thick one, and the 1 is the white. Okay, so just okay, and this one's because this is kind of like it's kind of the stuff they did in the summer. Plus a little bit of extra stuff that you need to be able to do this. I'm smart. Yes. Okay, so which ones would you like? Do you want both of them? Okay, do you want them today or do you want them tomorrow? Tomorrow? Yeah. Good stuff. Okay, I will get them and bring them in so we have them. Thank you. Perfect.